Next we have to see is the applications of Michaelson interferometer. The applications of Michaelson interferometer. So first application of Michaelson interferometer is applications number one is the measurement of wavelength, means unknown wavelength, measurement of wavelength, unknown wavelength, okay, lambda, measurement of lambda. So we can find out the wavelength of light, monochromatic light, with the help of Michaelson interferometer. So in this experiment, what we have to do, the monochromatic source whose wavelength is to be determined is kept at S. I have told you you know the figure. So the monochromatic source whose wavelength is to be determined is kept at the point S. When the mirror M1 and M2 are exactly perpendicular, M1 and M2 are exactly perpendicular, circular fringes are obtained. So when M1 and M2 are exactly perpendicular, then M1 and M2 dash again you should remember that M2 dash is nothing but virtual image of M2. So M1 and M2 dash are exactly parallel, and when M1 and M2 dash are exactly parallel, then the circular fringes will be observed. Okay. Then if the mirror M1 is moved forward or backward, the circular fringes appear or disappear at the center. Just now I have told you, appear or disappear at the center by moving the mirror M1. Okay. Now M1 is moved through a known distance D, and the number of fringes disappearing at the center is counted. For example, disappearing at the center or appearing at the center is counted. Suppose D1 is the initial thickness of air film between M1 and M2 dash. So D1 is the initial thickness. Of air film, that is distance between M1 and M2 dash. Then suppose D1 is the initial thickness of air film between M1 and M2 dash corresponding to bright fringe of the order N1. Okay. And D2 is the final thickness corresponding to the bright fringe of the order N2. Then we have twice D1 will be equal to N1 lambda. Twice D1 is equal to N1 lambda. Here we have considered the angle of reflection as very small, and therefore cos theta will be equal to 1. So twice D1 is equal to N1 lambda, and twice D2 is equal to N2 lambda. These two equations you will get. Now by subtracting the two equations, twice of D2 minus D1 is equal to N2 minus N1 and into lambda. Okay, or therefore now D2 minus D1 can be represented as D, and the N2 minus N1 as represented capital N into lambda, and therefore lambda can be written as twice D divided by N. This formula we can use for the determination of lambda. Now actually these few steps are used for the derivation of this equation, but to determine the lambda we can directly use this. Here lambda is the wavelength which is to be determined. D is number of rings which are appearing or disappearing at the center, that we can count. Okay, we can count, we can measure. And N, D is the displacement of the mirror M1, D. So we can measure the displacement. There is a precision screw arrangement to the mirror M1, and we can take the reading of that. And capital N is the total number of rings which are appearing and disappearing at the center, that we can measure, and therefore the wavelength can be determined. This is the one application. The second application of Michaelson interferometer is that we can measure a small difference between the two close wavelengths. For example, here if you use a sodium light, so in sodium light there are two lines which are called as D1 and D2. Okay, the one wavelength is lambda 1, and lambda 1 wavelength is equal to 5896 Armstrong unit. Means lambda 1 is taken as greater and another is lambda 2. So lambda 2 is equal to 5890 Armstrong unit. Okay. Lambda 1 minus lambda 2. So lambda 1 is the lambda 1 5896 and lambda 2 is equal to 5890 Armstrong unit. So these are the two close D lines, and difference between the two lines is equal to, that is we can have lambda 1 minus lambda 2 will be equal to how much? Only 6 Armstrong units. So difference is very small. So this difference can be measured with the help of Michaelson interferometer. Now here the procedure what we have to apply is, suppose here we have considering the lambda 1 is greater than lambda 2. Here lambda 1 we considered 5896 Armstrong unit and lambda 2 we considered 5890 Armstrong unit. So lambda 1 is greater than lambda 2. We have taken like this. If a source of light consists of two slightly different wavelengths, lambda 1 and lambda 2, then two sets of fringes corresponding to two wavelengths are produced in the Michaelson interferometer. Okay, by adjusting the mirror position M1, very bright fringes are obtained. Now when very bright fringes are obtained, then in this situation the bright fringe due to lambda 1 coincide with the bright fringe due to lambda 2. That is, the bright fringe due to lambda 1 coincide with the bright fringe due to lambda 2, and therefore we get a maximum brightness. Okay. When M1 is moved again, M1 is slightly moved again through a certain distance, the bright fringe due to 1 will be coincide with the dark fringe due to other, and due to this situation the fringes are blacked. That is, no fringes will be visible because bright fringe is coincide with the dark fringe, therefore intensity will be reduced. Okay, so dark fringes we will observe. Then again by moving mirror M1, a position is reached when both the bright fringes coincide and very bright fringes will be obtained. Okay, this is possible when the nth order of the longer wavelength coincide with n plus 1th order of the shorter wavelength, that is lambda 2, and therefore we can write twice d is equal to n into lambda 1. Okay, and again twice d is equal to n plus 1 into lambda 2. Okay, lambda 2 means shorter wavelength, lambda 1 is longer wavelength. Okay, so this equation, two equations we can obtain. Then therefore n lambda 1 is equal to, means twice d, left side is same, so right side will be equal. So n lambda 1 will be equal to n lambda 2 and plus lambda 2. Okay, now suppose I marked this equation as 1, that is twice d is equal to n lambda 1. This marked as 1 because we have to use this equation later on. Here this again we can simplify, so n common lambda 1 minus lambda 2 is equal to lambda 2. Okay, and therefore small n will be equal to lambda 2 upon lambda 1 minus lambda 2. Now we have to put this equation of n in equation number 1. So let us put this value. Therefore we get twice d, equation 1, twice d is equal to n, means we have to write this value. So lambda 2 into lambda 1 divided by lambda 1 minus lambda 2. We get this equation. Okay, or we can write lambda 1 minus lambda 2 is equal to lambda 1 lambda 2 divided by twice d, and lambda 1 minus lambda 2 is nothing but the difference between the two wavelengths, that is lambda 1 is higher, lambda 2 is lower, and therefore this is represented as delta lambda. So delta lambda will be equal to lambda 1 into lambda 2. Now we can see you have shown these values. Lambda 1 is 5896 and lambda 2 is 5890. Now the difference is only 6 Armstrong unit between the two. So approximately we can consider, for simplification, that both the wavelengths are approximately equal, and therefore lambda 1 into lambda 2 can be used as a lambda square. So this is equal to lambda square and divided by twice d. So this formula we can use for the calculation of small difference between the two wavelengths, where lambda is average value of lambda 1 and lambda 2, where lambda is equal to lambda 1 plus lambda 2 and divided by 2. That is the average value of lambda 1 and lambda 2. So this equation we can use. Here lambda is the average of lambda 1 and lambda 2, therefore we can calculate, and d is the displacement of mirror M1. So that we can measure with the knob which is available with the mirror M1, and from the knob, means micrometer screw, we can take the reading, initial reading and final reading. Okay, so after knowing lambda and d, we can calculate the difference, small difference between the two wavelengths. Okay, so these are the two applications of Michaelson interferometer, and both the applications are very important. Some numericals are also available on these two applications. So in the book also the several number of solved numericals are given. So I request you to go through that solved numericals from the book. Thank you.